Hi, I'm Bob. We have done the first two parts of the problems at the end of Chapter 2, the simple linear regression model, in the textbook Introductory Econometrics, a modern approach, the 7th edition. Today, let's complete the last 6 problems. Here the problem number 13. Let y be any response variable and x a binary explanatory variable. The sample size is n. Let n0 be the number of observations with xi equal to 0 and n1 the number of observations with xi equal to 1. Let y bar 0 be the average of yi with xi equal to 0 and y1 bar the average of yi with xi equal to 1. The first question asks us to show the following equations. The total number of observations is n. Suppose the number of observations with x equal to 1 is n1, and the number of observations with x equal to 0 is n0. The sum of n1 and n0 is n. For the first question, the sum of xi equals the sum of n1 ones and n0 zeros. That is n1. The sum of 1 minus xi equals n minus the sum of xi. That is n minus n1, which is n0. The sample mean of x is equal to the sum of xi divided by n, which is n1 over n. 1 minus x bar is n0 over n. The sample mean of x is the fraction of observations with x equal to 1. The second question is to argue that the average of yi with xi equal to 0 can be written as follows. I would like to first show the structure of the data by listing the observations. We can always sort the observations this way with xi equal to 0 before xi equal to 1. Then the average of yi with xi equal to 0 can be written as 1 over n0 times the sum of the first n0 yi's. The average of yi with xi equal to 1 can be written as 1 over n1 times the sum of the remaining yi's. We can show the equation from the right to left. The right-hand side of the equation can be expressed as two parts. The first part contains observations from 1 to n0, and the other part has the remaining observations. The second part sums to 0 because all xi's in the second part are 1. The first part is the sample mean of yi with xi equal to 0. We use the same method to show the second equation. The right-hand side can be decomposed into two parts. The first part is 0, and the second part is the sample mean of yi with xi equal to 1. The third question is to show that the average of yi in the entire sample, y bar, can be written as a weighted average. On the left-hand side is y bar. It can be expressed in two parts. The first part is the sample average with yi with xi equal to 0. That is, the first n0 observations. The second part is the sample average of yi with xi equal to 1. That is, the remaining n1 observations. We can show that the first part equals the first term on the right-hand side. The first term on the right-hand side is 1 minus x bar times y0 bar. We substitute y0 bar with expression from the last question. After some algebra, we obtain the answer. Similarly, we show that x bar times y1 bar is equal to the second part of y bar. Therefore, the weighted average equation holds. The fourth question is to show that when xi is binary, the following equation holds. The key is that for a binary variable xi squared equals xi. So the first term on the left-hand side becomes the sample mean of xi. And then we obtain the equation. In the fifth question, we will show the following equation. I expand the product on the right-hand side to 4 terms. For the expression on the left-hand side, I first focus on the minus x bar times y bar term. Using the result from the third question, I substitute y bar with the weighted average, and the result has 3 terms. I compare them with the 4 terms on the right-hand side and find they are the same. So we just need to show a simple equation. In the left-hand side, I decompose the summation part into 2 terms. The first term is for the xi equal to 0, and the second term is for the xi equal to 1. So the first term is 0. The second term is n1 over n times y1 bar. On the right-hand side, x bar times y1 bar equals n1 over n times y1 bar 2, because x bar is n1 over n, the result from the first question. Therefore, the original equation is true. The sixth question is to use the result from the above 2 questions to obtain the 2.74 formula for the beta hat 1. The beta hat 1 is the difference in the sample means of the outcome variable in the 2 different states of the world. We show this result from the standard formula for the slope estimator. We can write out the squared term of the denominator, and it equals x bar times 1 minus x bar. We can also expand the numerator, and it equals x bar times 1 minus x bar times y1 bar minus y0 bar. Finally, we prove that beta hat 1 is the difference in the sample mean of the outcome variable in the 2 different states of the world. The seventh question is to derive equation 2.73. Beta hat 0 is the sample average of yi with xi equal to 0. I start with the standard formula of the OLS intercept estimate. Then I plug in the result of the beta hat 1 and write beta hat 0 as a function of x and y. Since y bar can be expressed as a weighted average, I replace the y bar with this weighted average. And finally, I have the 2.73 equation. The intercept estimate is the sample mean of the outcome variable when x equals 0. Next, let's do problem 14. In the context of the last problem, suppose yi is also binary. For concreteness, yi indicates whether worker I is employed after a job training program, where yi equals 1 means has a job, yi equals 0 means she does not have a job. Here, xi indicates participation in the job training program. Argue that beta hat 1 is the difference in employment rates between those who participated in the program and those who did not. From equation 13, we have beta 1 hat equals the difference in the sample means of the outcome variable in the two different states of the world. Here in this example, suppose N0 workers did not participate in the training program, that is, xi equals 0. Then y bar 0 is the average value of yi for the workers without training. Since yi is binary, indicating whether the worker is employed, y bar 0 is the fraction of workers who are employed for this group of workers without training. Similarly, y bar 1 is the fraction of workers who are employed among the workers with training. The fraction is the employment rate in this example. Therefore, beta hat 1 is the difference in the employment rates between those who participated in the job training program and those who did not. Let's go to problem number 15. Consider the potential outcomes framework, where yi0 and yi1 are the potential outcomes in each treatment state. Show that if we could observe yi0 and yi1 for all I, then an unbiased estimator of the population average treatment effect could be as follows. It is sometimes called the sample average treatment effect. We write down the population average treatment effect formula. The population average treatment effect is the expectation of the difference between the outcome variable in the two different states of the world. We imagine we could observe yi in both states of the world. We need to prove that the sample mean is an unbiased estimator for the population average. We do it by showing the expectation of the sample mean of yi in the first state equals the population average of y in that state. Similarly, the sample mean of yi in the second state equals the population average of y in that state. So, the sample mean treatment effect is an unbiased estimator of the population average treatment effect. In the second question, we need to explain why the observed sample means y bar 0 and y bar 1 are not the same as population means. I would like to use the structure of the data to show why. Suppose the first n0 observations have xi equal to 0 and the remaining n1 observations have xi equals to 1. Then we denote yi in the first n0 observations y0 and denote yi in the remaining n1 observations y1. The sample mean of y0 is computed using the first n0 observations, and the sample mean of y1 is computed using the remaining n1 observations. By contrast, the population average of y in each state should be computed using the entire sample because we imagine that we observe both states of the world for each individuals. Let's do problem 16. In the potential outcomes framework, suppose that program eligibility is randomly assigned, but participation cannot be enforced. To formally describe this situation, for each person I, Zi is the eligibility indicator and Xi is the participation indicator. Randomized eligibility means Zi is independent of the outcome in each state, but Xi might not satisfy the independent assumption. The first question is to explain why the difference in means estimator is generally no longer unbiased. Xi is the participation indicator, and it might not satisfy the independent assumption. So the zero conditional mean assumption does not hold. When individuals can choose whether they participate in the program or not, the explanatory variable participation might be correlated with the unobserved factors contained in the error term. The difference in means estimator beta hat 1 is generally no longer unbiased. The second question, in the context of a job training program, what kind of individual behavior would cause bias? In the context of a job training program, the explanatory variable is the trailing binary variable. The outcome variable is the employment status of the workers. The other unobserved factors contained in the error term include workers' health, educational attainment, and marital status. These factors affect the worker's probability of being employed. They are also correlated with whether the worker chooses to participate in the job training program. In other words, if the workers can choose whether to take part in the program, the zero conditional mean assumption will be violated. For example, a better educated worker is more likely to take a job training course because it is easier for her to pass it. A better educated person is also more likely to find a job. If this is the case, educational attainment is positively related to both the outcome variable and the explanatory variable. Therefore, it leads to an upward bias of the OLS estimate for the trailing effect on employment. Now we reach problem 17. We can write error term as the weighted average. The first question is to find the variance of the error term conditional on x. We can write out the variance into two terms because the covariance term is 0 under the zero conditional mean assumption. We simplify the squares terms, and then we can write the conditional variance as a weighted average of the variances from the two different states of the world. The second question is to find when the conditional variance is constant. There are three cases in which it is a constant. Case 1 is when all xi's takes on the value 0. The second case is when all xi's are 1s. In these two cases, all xi's are in the same state of the world. The third case is when the variances are the same for the two different states of the world. Eventually, we reach the final problem. Let x be a binary explanatory variable, and suppose the probability that x is 1 is ρ. Ρ is between 0 and 1. First question. If we draw a random sample of size n, find the probability, call it gamma n, that assumption SLR3 fails. Argue that as n approaches infinity, gamma n approaches 0. The simple linear regression assumption number 3 is about the sample variation in x. There must be some variation in x to obtain the OLS estimates. The failure of this assumption means all x takes on the same value. The probability of one observation with xi equal to 1 is ρ. The probability of n observations with xi equal to 1 is ρ to the power n, if all observations are independent and identically distributed. The probability of n observations with xi equal to 0 is 1 minus ρ to the power n. As n approaches infinity, ρ to the power n approaches 0, and 1 minus ρ to the power n approaches 0. That is to say, the probability that simple linear regression assumption number 3 fails approaches 0. The second question is to compute the probability for ρ equals 0.5 and n equals 10 and 100. Discuss. If ρ equals 0.5, n equals 10, the ρ to the power n is 0.000977. When n is 100, ρ is tiny, which is 7.89 times 10 to the power minus 31. As the number of observations increases, the probability that x has no variation approaches 0. In other words, the likelihood that all observations are in the treatment group or all of them are in the control group is 0. The last question is to do the calculations with ρ equal to 0.9. How do your answer compare with part 2? If ρ is 0.9 and n is 10, ρ to the power n is 0.349. If ρ is 0.9 and n is 100, ρ to the power n is 0.0000266. Here, we suppose the probability of assignment to the treatment group is much higher than to the control group, or vice versa. On the one hand, the sample size should be relatively large to ensure the variation assumption, simple linear regression assumption number 3 holds. On the other hand, we don't need a very large sample. A sample with 100 observations is okay. Thank you so much for doing the problem set with me in these 3 videos. Hope the solutions help. See you. Thank you for watching this video and subscribing to my YouTube channel. See you next time.